How do you ensure that your network traffic is secure with today's ever-evolving threats? Utilizing a network security appliance to do that is a great step. Cisco's Adaptive Security Appliance, or ASA, has been one of the most popular firewalls in use by organizations throughout the world. Rebranded as Secure Firewall ASA, it is still a popular network security appliance for many enterprises to secure their traffic. Hi, my name is Craig Stansbury, and I'm excited to show you how to deploy a Secure Firewall ASA to secure your network. Before you get into configuring the ASA, it's a good idea to understand how the Secure ASA is designed to be used. The ASA was first released in the early 2000s, and it combined the features of multiple security appliances into one device. When most people think of an ASA, they think of a network firewall, which was how I first used the ASA when I started in network security. But it also has other features, such as a VPN concentrator. This used to have to be a separate device, but being able to configure remote access and site-to-site VPNs without needing another device is quite valuable. Combining the Secure Firewall ASA with the Firepower module allows the device to also have intrusion detection and intrusion prevention capabilities as well. And integrating the firewall with other security tools allows it to secure traffic going to the internet, not just securing traffic based on ports and IP addresses. And while it is a separate device, the Cisco Firewall ASA does have a similar feel to a Cisco iOS CLI, so a lot of engineers familiar with Cisco don't feel lost. However, you can also use a GUI to manage the ASA, which is called the Adaptive Security Device Manager, or ASDM. Something that is different about the ASA compared to iOS devices is that you need to name each interface. So for example, if Gigabit Ethernet 00 is connected to the internet, you might name that interface outside. And the firewall uses the interface name as well as the security level assigned to the interface to make policy decisions. Speaking of security levels, these are used to tell the ASA how to secure the devices that sit off of each interface. Security levels can be anything between 0 and 100 inclusive, and the higher the security level, the more secure the ASA considers devices that hang off that interface. So a security level of 100 is typically used for corporate devices, or quote, the inside network. A security level of 0 is usually used for a public-facing interface. And by default, traffic flowing from a higher security zone to a lower security zone does not require an explicit ACL. It is inherently allowed by the ASA. Conversely, if you need traffic to flow from a lower security zone to a higher security zone, this will require an explicit ACL rule. So let's walk through what you will see configured. Here is the Secure Firewall ASA. And first, you need to manage the device. For this lab, the ASA will connect to the out-of-band management network and use the Management 00 interface to do so. The name of this interface will be MGMT, and the IP address will be 172.20.1.61 with a 24-bit subnet mask. Next, the ASA will use Gigabit Ethernet 00 to connect to the internet. The name of this interface will be Outside, and it will have an IP address of 204.8.1.66 with a 28-bit subnet mask. The default gateway for the ASA will be the IP address of the ISP, which is 204.8.1.65. Gigabit Ethernet 01 will connect to the inside router. The name of this interface on the ASA will be Inside, and it will have an IP address of 192.168.18.1 with a /30-bit subnet mask. While the router is already pre-configured for this course, it will have the other IP address in the /30 on its interface Gigabit 00, and the ASA and router will use EIGRP for dynamic routing. And connected to interface 01 of the inside router is the user subnet, which is 192.168.17.0/24. Finally, Gigabit Ethernet 02 will connect to the DMZ network. The IP address on the ASA will be 10.100.1.1/24, and the name of this interface will be DMZ. And the last thing that I'll say is I'm using the ASA and iOS images from Cisco Modeling Labs, and I'm running them using EVE-NG for my lab environment, along with my ES6i host. I highly encourage you to follow along and configure an ASA in your own environment, as I believe that is the best way to gain deep understanding of the concepts that are being taught. If you are unsure how to use EVE-NG or get the images from Cisco Modeling Labs, I recommend watching the Create a Home Networking Lab Using Network Emulation course that I created. This course will walk you through how to get these images and configure various network emulation environments if you want to get that set up to follow along. I've already pre-staged some of my EVE-NG topology, and as you can see, I already have a virtual iOS router in here, and it's connected to the inside network, which just connects to other computers running on my ESXi server. And then I already have an out-of-band management network, which connects to the 172.20.1.0 network. I have my DMZ network, which again, servers on my ESXi host are part of this network. And then finally, I have a network that represents the internet, and this network is configured on my home router, but for this lab, it'll simulate an ISP. So let's go ahead and drop in our Cisco Adaptive Security Appliance. And again, I'm just going to right click and then click on Node. And then I'm going to search for ASA here and then click on my Cisco ASA. And I'm just going to change this name to Global ASA 1. Then I'll leave everything else set to the default. So let's go ahead and scroll down and then click Save. And go to arrange this here so it looks more symmetrical. All right, so now let's go ahead and start adding some links. First, I'm going to connect to the out-of-band management network. And for the interface, I'm actually going to choose the built-in management interface. So I'll go ahead and select that and then click Save. And let's go ahead and configure Gigabit Ethernet 00 to connect to our ISP. So again, I'll draw that link. And then by default, it's selected on Gigabit Ethernet 00. Go ahead and click Save there. Gigabit Ethernet 01 is going to connect to our inside router. So again, I'll grab that link icon, pull it over. And so on the ASA, it's interface 01. And on the inside router, it's interface 00. That all looks good. So I'll click Save. And then finally, let's go ahead and add a link to our DMZ network. And on the ASA, it's going to be interface Gigabit Ethernet 02. Again, that looks good. So go ahead and click Save. And now that we have our topology set, again, let me just go ahead and make this a little more symmetrical. There we go. And the last step here is to turn on these devices. So I'll right click each one and then click on Start. I'm going to go ahead and pause this video and come back once this ASA has completely booted up. All right, the ASA is finished loading, so let's go ahead and configure it. And I am using an image from Cisco Modeling Labs. And since I'm not going to license it as if it was in production, that's perfectly legal. However, the throughput will be limited to only 100 kilobits per second. Should be just fine in a lab environment, but just know if you're also using an image you got from Cisco Modeling Labs, the throughput will be limited. First, I'm going to enter enable mode. And as you can see, we are prompted to configure a password now. However, some ASAs will already have a password configured, so they'll prompt you to enter that. And if that's the case, there is no password, just hit enter and you can configure it later with the enable secret command. In our case, I'm going to go and enter the password of global123 with a capital G. So now that that's set, let's go ahead and configure this. So I'm going to enter configuration mode. And for anonymous error reporting, I'm going to enter no. I'll change the host name to global ASA1. Now let's configure that management interface. So I'm going to go into interface configuration mode and specify management 00. And I'm going to give an IP address of 172.20.1.61 with a 24-bit subnet mask. Let's go ahead and enable this port. And I wanted to show you that we're not quite done because we can't quite ping this interface, and I just want to show you why. So if I enter command prompt, and then I try to ping that IP address that we just set, even though that IP address is set on the interface, there's still a few more things that we have to do. So let's go back to our configuration. The first thing we're going to do here is name this interface. And to do that, we use the command nameif, and I'm going to specify mgmt. As you can see here, the security level is set to 0 by default, which is fine. That's telling the ASA to keep this interface secured and only allowing traffic that we specify. The last thing we need to do on this management interface is just enter the command management-only. What this does is completely puts this interface on its own routing domain And to show you what I mean, if I enter show route, you can see here there are no routes because the generic command of show route is showing the data plane. But if I enter the command show route management-only, you can see that the ASA knows about the 172.20.1.0 network via the management interface. I'll save the changes. So now if I go back to the command prompt and try to ping the ASA, now we are successful. Even if you're able to ping the ASA, there's still more steps you need to configure in order to SSH to it. To show you what I mean, if I try to open another PuTTY session, I'll type in the management IP address of the ASA. And if we give this a few seconds, you can see that we are not able to establish a connection. So go ahead and click OK, and then let's jump into the ASA and configure those settings. Go ahead and pull this up here. All right. The steps to configure SSH on an ASA are similar to another Cisco iOS device if you are familiar with that. So the first thing that we need to do is to give this a domain name, and I'm just going to specify globalmantics.com, but you'd specify any domain name that you want to use. All right, from there, we need to generate the crypto keys. There may already be some generated, but just to show you that command, it's crypto key generate, RSA, and you can use a higher modulus if you want to, but for this lab environment, I'm fine with 2048, and it is asking me if I want to replace that RSA key pair, and I am fine, so I'll go ahead and enter yes. And then from there, we're going to enable SSH version 2, and the command for that is pretty simple, just SSH version 2. You need to specify the Diffie-Hellman group, and the command for that is SSH key-exchange, and then the keyword group. And if I hit a question mark, you can see that this ASA has a few options. I'm going to go with the most secure, which is DH-group14-SHA-256. The next step is to create a username, password, and privilege level for all the users that want to connect. This can be done through Radius, but for this example, just to get the ASA up and running, I'm going to create a local user. So I'll enter the command username and then specify my username of Craig and then enter the keyword password and then specify a password of global123 with a capital G. And then finally, I want to use privilege 15, which is the most privilege and will allow me to enter any command on this ASA. From there, you need to tell the ASA to use this local database for anyone that is trying to connect to the ASA. You do that with the command AAA and then authentication. And then we're going to specify SSH since that's what we're configuring now. Actually, let me go ahead and back out of this. And if I enter a question mark, you can see this is a similar command for all HTTP connections, but actually that's a misnomer because that's HTTPS as well as SSH and then even Telnet, which I highly advise that you don't use. And as you can see, I got that warning message. Again, let me know that this ASA is licensed only for a lab environment. So let me go ahead and hit enter so I can see where I was. And if I use the up arrow, now this time I'll specify SSH, and then we're going to enter the keyword console. And then we're going to specify the local database with the word local, all in capital letters. The last thing that you need to do is to tell the ASA which IP addresses can connect to the ASA over SSH and which port you're allowing those connections to come in through. This will help ensure that not just anyone can establish a connection, they need to have the right IP address, which is where an out-of-band management network really can be beneficial here. At any rate, that command is SSH to specify the protocol they are using, and then finally the network and subnet mask of where the administrators will connect from. So I'll enter 172.20.1.0 with a 24-bit subnet mask. And then the last step is to specify the interface, and again, we're going to use that management interface. All right, that all looks good. Let me go ahead and save these changes. And then let's go ahead and try to reestablish that PuTTY connection. So I'm going to go ahead and right click and then click restart session. This computer is prompted to accept those keys we just generated. So I'll go ahead and click accept. And then from here, I'm going to use username I created, which is Craig, the password of global123 with a capital G. And then if I enter enable, just go ahead and enter the password that was configured either when you set up the ASA or when you manually used the enable secret command. Let's start this demo out by showing what we're working with. So if I enter the command show interface IP brief, you can see that gigabit Ethernet 00 through gigabit Ethernet 02 are all unassigned. So let's go ahead and fix that. I'm going to enter configuration mode and then go into interface configuration mode for gigabit Ethernet 00. And just like with an iOS router, I'm going to enter the command IP address followed by the address of 204.8.1.66 with a 28-bit subnet mask. And I'll enable the interface by entering no shut. And so now, unlike an iOS router, you need to tell the ASA the name of this interface. So to do that, I'll enter the command nameIf and then specify the name that I want to give this interface. So this will be outside. And as you can see, the ASA automatically applies a security level of 0 by default for this interface. So now let's move to the inside interface, which is going to be gigabit Ethernet 01. Let's go ahead and name this interface as well. And this time I'm going to use the interface name of inside. And this time the ASA automatically sets the security level to 100 by default. So just know that the ASA will automatically set any interface with the name of inside to 100, again to allow that traffic to easily flow from the inside to the outside or any less secure security zones. All right, let's finish this interface configuration by giving it an IP address of 192.168.18.1 with a /30 subnet mask. And then enable the interface. And then finally, let's configure that DMZ interface. Again, that's going to be interface gigabit Ethernet 02. And I'll go ahead and name this interface DMZ. And as you can see, this is set to a security level of 0, but we want all traffic from the DMZ to be able to flow out to the internet without configuring an ACL rule. So in order to do that, I'm actually going to change the security level. You do that with the command security-level, and then specify the level that you want. In this case, I'll enter 50. So now traffic from the inside can flow to both the DMZ as well as the outside, since it's the most secure, and then the traffic from the DMZ can flow to the outside, since the outside is less secure than the DMZ, but traffic cannot flow from the DMZ to the inside without an explicit ACL rule, again because the security level for the DMZ is less secure than the inside. All right, finishing this one off, I'm going to give it an IP address of 10.100.1.1 with a 24-bit subnet mask, and again, I'll enable the port. Now that all the interfaces are configured, I'll exit out of interface config mode, and then let's take a look at the interfaces now. You can see that the interfaces have been configured and they're all shown as up. And if I enter the command show nameIf, you can see each interface also has the appropriate name as well as the security level, so that all looks good. And if I enter show route, you can see all the locally connected routes. However, let's configure EIGRP. This is very similar to configuring it on an iOS device, so the command is router EIGRP and then specify the autonomous system number of 100. Then I'll enter no auto summary. And then I'll configure the networks that we want to advertise. Again, you do that with the network keyword. And then I'm going to specify the inside network, which is 192.168.18.0. And unlike an iOS device, you don't use a wildcard mask, you just use the normal subnet mask. In this case, it's going to be a /30. And then let's go ahead and specify that DMZ network as well, which again is 10.100.1.0/24. All right, let's go ahead and exit out of this. And then since this is a security focused course, using keys for the EIGRP neighbors should be leveraged. This is done per interface. So in this case, the only interface that needs configured is the inside network. So I'll go into interface configuration mode, and the command to set the key is authentication key, then specifying EIGRP and the autonomous system number of 100. And I'm going to specify the key itself, which in this case, I'll just use global123 with a capital G, and then use the keyword key-ID, and then set the key ID to the same key ID that is configured on the router. So in this case, that key ID is 1. And then I'll hit enter. So make sure that not only the key matches, but also the key ID. Then you need to tell the ASA to use MD5 hashing on this interface, and that command is authentication mode EIGRP, again specifying the autonomous system number of 100, and then entering the keyword of MD5. Now that authentication is configured, I'm going to exit out of the interface config mode. And the last thing I want to do is to set everything to go to the internet. so I'm going to enter a static route. On the ASA, that command is route, and then you have to specify which interface you want to send the traffic out. And again, you're going to use the name of the interface, not the interface number. So in this case, I'll enter outside rather than gigabit Ethernet 00. And then from here, it's like normal, specify the network and the mask. So I'll use quad zeros, and then specify the next hop of the ISP, which again is 204.8.1.65. All right, let's go ahead and take a look at our route again. All right, here's that static route that we just configured using the outside interface. And then EIGRP does look to be working because we have a route here for the inside network of 192.168.17.0. And to make sure that everything is working as expected, I'll jump over to an inside computer. Let's go ahead and open up a browser. And then first, I'm going to navigate to the internet. So I like to use fast.com. All right, that connection is established, but unfortunately, we are limited to that 100 kilobits per second. So let's go ahead and let this run through. All right, so this looks good, even though it's very slow. And then let's make sure we can get to our DMZ network. So I'll open up another tab and then navigate to Global Mantix's web server. All right, and that is loading as well, albeit very slowly. So it looks like our data plane routing is working as expected. If you want to use Cisco's ASDM to have a GUI management for the ASA, the first thing that you should know is that ASDM communicates with the ASA via HTTPS. So the first step is to enable the HTTPS server, and then just like you have to do to enable SSH access, you need to tell the ASA which IP addresses can connect to it via HTTPS, and then also tell the ASA what to use for authentication. So first, I'll verify that I cannot get to the ASA via HTTPS, and just as I expected, this page did not load. So I'll go to the CLI to configure the ASA for HTTPS access. I'll enter configuration mode, and the first command that you need to enter is HTTP server enable. And this is slightly a misnomer since it really is enabling HTTPS, but on the ASA, the keyword is actually HTTP. And just like with SSH, you have to specify which IP addresses are allowed to access this ASA over HTTPS. Again, I want to limit this to devices that sit in the out-of-band management network. The command is very similar as the one allowing SSH access, except this time the keyword is HTTP, followed by the IP address and subnet mask that you want to allow access from. So in this case, it's 172.20.1.0 with a 24-bit subnet mask. And finally, specifying that interface that you want to allow connections in on. In this case, that's going to be that management interface. The last step is to tell the ASA how to authenticate users. Again, the command is very similar to the SSH command. So it's AAA authentication, this time specifying HTTP, then the keyword console, and telling it to use the local database. That's all you need to configure on the ASA. So let's go back to our browser. And if I try to refresh this page, all right, we are prompted with a security warning, and that's just saying that we're using a self-signed certificate. So we're good to accept the risk and continue. We can see the version of ASDM that this ASA has on it. So I'm going to go ahead and install the ASDM launcher by clicking this button here. I'm going to log in with my username as well as my password. Then once I'm signed in, I'm allowed to download the file. So I'll just click Save File. And now that that file is downloaded, I'm going to go ahead and open it up, run through the install process. So click OK. And it's pretty much a next situation. And my computer's prompting me to make sure I want to allow this install, which I do. So I'll go and click yes. I did want to point out that you do need to have Java installed and running on your machine in order to use ASDM. The install is completed, so I'll go ahead and click Finish. An ASDM automatically pops up. That is the management IP address of our device, so that looks good. And then again, enter your username and password. Again, with that self-signed certificate, this is untrusted. In a lab environment, this is perfectly safe, so I'll go ahead and click Continue. And then it takes about 20 to 30 seconds for the ASDM to pull the config from the ASA and then pull it up in the ASDM GUI. The last step that I like to do is to enable the CLI output when we're pushing a configuration from the ASDM. So to do that, go to Tools, and then click on Preferences, and then ensure this box here is checked, preview commands before sending them to the device. All right, that looks good. I'm up and running to use ASDM to manage my ASA. In this demo, I'm going to show you how to configure an ACL rule as well as a couple of NAT rules. To do that, you're going to click on Configuration, and then we're currently in Device Setup, but to configure ACL rules and NAT rules, you need to click on Firewall. The first tab here is Access Rules, but first I actually want to create the NAT rules, so that way we know we're good to go. The first NAT rule that I want to create is to allow all internal traffic to be NATed to the public IP address of the ASA. I'm going to go ahead and click Add. The source interface is going to be set to the inside since that's where this traffic is going to come from. And the source address, I recommend using a network object. By default, any of the ASA's connected interfaces automatically have a network object created for them, but since the users hang off the router and not the ASA itself, we need to manually create that network object. To do that, I'm going to click the three dots, and then I'm going to click Add to create that network object. For the name, I'm going to enter user subnet, and the type is not a host, it's actually going to be a subnet, so I'm going to click Network, and the IP address is 192.168.17.0, and that's all I need to do for that network object, so I'm going to click OK, and then go ahead and select that object by double-clicking on it, and then clicking OK again. All right, so now we're using the user subnet, and the last thing you need to do is to change the source NAT type from static to dynamic with port address translation, and then specify what the source address needs to be translated to. And you could create another network object, but I just want to translate it to the IP address of the outside interface, so double select that, and then click OK. And as you can see here, the destination interface automatically changed to the outside, since logically, that's the only way that this rule would work. All right, that looks good to go, so go ahead and click OK. And just to see what it looks like, if I click Apply, here is the exact command that you would need to enter if you wanted to do this via the CLI and not ASDM. So I'm going to go ahead and send this command. All right, so the next NAT rule that I want to create is for anyone on the internet to get access to Global Mantix's web server. So to do that, we need to tell the firewall a public IP address that it can use to then NAT to the original IP address of the web server. This is pretty simple as well. I'm going to go ahead and create another network object and then configure the NAT within that object. So I'll go ahead and click Add, and then Network Object, and for the name I'm going to enter Global Web 01, and this time it is a host, and the real IP address of this server is 10.100.1.11, and then here I'm going to expand NAT, and first I'll enable an automatic address translation rule. The type is going to be left set to static. The translated address, I'm going to use an IP address that's on the same network range as the outside interface. So for this example, I'll use 204.8.1.67. So if you don't change anything else, this tells the firewall anytime that server goes to the internet, translate it to this IP address. However, to create the reverse rule, which is what you would need for any internet user to access this web server, click on Advanced. And then here I'm going to specify the source interface would be the DMZ, the destination interface would be outside. And by getting granular here with the source and destination interface, when the ASA automatically creates a reverse rule, it'll be exactly what you need. If you needed to, you could translate the port as well, but I just need to translate the IP address, so go ahead and click OK, and then click OK again. And as you can see here, even though I configured this inside of the network object, the ASA automatically created a quote network object NAT rule. And as you can see, the second line of rule 2 says the source interface would be outside, the destination interface would be DMZ, the source address would be any, which makes sense since we don't know what IP address any web users would be coming from, but the destination is a publicly routable IP address of 204.8.1.67. And then as you can see, the translated packet is going to change that destination to the IP address of Global Web 01. I'll go ahead and click Apply so you can see what that CLI would look like. So let's go ahead and send it. And just to verify that the ASA is indeed blocking external traffic into a more secure zone, I'm just going to make sure that we cannot get to this web server until we add that ACL rule. So go ahead and open up a browser. And then this management computer does sit in the out-of-band management network. So in order to get into the DMZ network, I'm going to use my home router to go in through this internet network, through the ASA, and down through the DMZ. So that's what the traffic looks like. So go and open a new tab and then enter HTTP and that IP address that we just configured to be NATed, which is 204.8.1.67. All right, it looks like the ASA is doing its job and blocking that traffic. So let's go ahead and create that ACL rule. We'll go back to ASDM. And this time I am going to go to access rules. And just to make this look a little bigger so we can look at it here, I'm going to go and expand it. And as you can see, by default, any more secure zone automatically allows access to the less secure networks. So that's why you don't need to create a rule for the inside users to get to the internet. All right, we do want to create a new rule for the outside zone. So go ahead and click add. And the interface that it's going to be coming in on is the outside interface. The source IP address is going to be any. The destination IP address, you need to use the real IP address of Global Web 1, or put another way, thinking from the network traffic flow, this is going to be the post-NAT IP address. The pre-NAT IP address is that public IP address that we created, but after it's NATed, it's going to be this address here of 10.100.1.11. So go ahead and double click that to select it, and then click OK. And let's just lock down this rule a little tighter. Instead of IP address, I'm going to use the HTTP protocol. There's already a service object created, so I'm going to go ahead and select that. And that's all you need to do to configure your first ACL rule. So go ahead and click OK and apply these changes. And this is what the CLI rule looks like. The first one is creating an ACL rule itself. And the second line is adding this ACL rule to the outside interface. Let's go ahead and send it. I'll go back to my web browser. Again, try to establish that connection. And this time I'm allowed through the ASA, again hitting that NATed IP address. If I jump over to an inside computer, go and open up the web browser. And again, I'm going to try to go to fast.com just to verify that that NAT translation is working. All right, that connection was established. Let's open up the CLI. If I enter the command show xlate, we can see that the IP address of the inside computer is indeed being translated to the IP address of the outside interface. And if I go back to ASDM, sure enough, you can see that this ACL rule has a few hits. Virtual private networks are one of the most common features that organizations use a secure firewall ASA for. So let's walk through the components necessary to configure a site-to-site VPN on an ASA. The first component necessary is to define the traffic on both the local side and the remote side that will traverse the VPN. On the ASA, the VPNs are policy-based rather than routing-based. So what this means is the exact traffic flowing over the VPN needs to explicitly be called out in a policy. That is done in an ACL line permitting the local and remote side, and that ACL is called later in the VPN configuration. Next, the VPN needs to reference group policy settings for the VPN. These settings can specify the tunneling protocols, idle timeout settings, and the maximum connection time for the VPN. If the group policy doesn't specify these values for a particular VPN, then the VPN will just use the global defaults. You also need to specify the tunnel group settings. This tells the ASA what type of VPN it is, what the pre-shared keys are if you're using them, as well as the keep alive metrics. It also is what ties the group policy settings to the VPN. And the crypto policy settings also need to be determined. This is for both the IKE tunnel as well as the IPsec tunnel that is built on top of the IKE tunnel. Finally, there are the rest of the crypto map settings. These associate all of these other components together for the VPN, as well as telling the ASA which interface to use to establish the VPN and the IP address of the remote VPN peer. While the IKE policies are required for a VPN to work properly, they are not specified per VPN. All of the IKE policies are configured globally, and when the ASA tries to establish a VPN, it will work its way down the IKE policy list, and it will choose the first policy that matches a policy of the remote peer. So make sure to have your most secure IKE policies you are using listed first, so that way a less secure policy isn't inadvertently chosen. For my lab, I have global ASA 1 with the outside IP address of 204.8.1.66, and a VPN will need to be created to the branch ASA, with an outside IP address of 204.8.1.81. The traffic that we'll need to protect on the local side is both the 192.168.17.0/24 network as well as the 10.100.1.0/24 network. And on the remote side, I will protect the 192.168.20.0/24 network. So these networks will be called out in that crypto map ACL. So the VPN will be created by each ASA pointing to the outside IP address of the peer ASA. The VPN will be a site-to-site VPN, and that is specified in the tunnel group settings, and I only want to use IKE version 2 since it's been around for quite some time, and so that will be specified in the group policy settings. Every other group policy setting will use the ASA's default, and for authentication, I will keep it simple and use pre-shared keys rather than device certificates. For the IKE policy, I'll create a new policy and set it as the highest priority since it'll be the most secure policy on the ASA, and I want the ASA to use it first. Following the Hagel acronym, the hash will be SHA-256, authentication we already covered, Diffie-Hellman group will be 14, lifetime will be 1 day or 86,400 seconds, and the encryption will be AES-256. The IPsec proposal will use SHA-256 for the hash and AES-256 for the encryption. And I will use perfect forward secrecy of Diffie-Hellman group 14. I wanted to point out that all these settings have been pre-configured on that branch ASA, with the only difference being that the local and remote traffic has been swapped in its crypto map ACL, and the branch ASA will point to the outside IP address of Global ASA 1. And finally, there are already NAT rules in place on Global ASA 1 for traffic sourced from the user subnet and DMZ subnet going out to the internet, so a NAT exemption rule will need to be created. So that way, the real IPs are sent over the VPN. On an ASA, there are multiple ways to configure site-to-site VPNs. The first is to use the CLI. The second way is to go to Configuration and then click on Site-to-Site VPN. And then from here, you just click the Add button. But I'm going to use the VPN wizard and walk through all the components in there. So to do that, click on Wizards, and then VPN Wizards, and finally, I'm going to click on Site-to-Site VPN Wizard. This first page here is just an introduction page, so I'm going to go ahead and click Next. And on this page, you need to tell the ASA the IP address of the remote ASA peer that you're connecting to. So for me, that's going to be the IP address of the outside interface of our branch office ASA. So that's 204.8.1.81. And then, of course, you need to tell the ASA which interface to use in order to establish this VPN. And most often than not, that's always going to be that outside interface. So that looks good. So go ahead and click Next. Now the ASA is wanting to know which traffic we want to protect both on our local side as well as the traffic on the remote peer. And these are the networks that will be added in the CryptoMap ACL. There are two different ways to do it. You can just put each individual network object. So in this example, I'd type in user, and then select user subnet, add a comma, and then type in DMZ, and then use that DMZ network object. But honestly, this isn't my favorite way to do it. My personal preference is to not add each individual network object, and I'll show you why. So let me do it the way that I prefer. So I'm going to go ahead and back out of this, and then if the network object group is not already created, just go ahead and click the three dots here. And then I'm going to go ahead and click Add, and then select Network Object Group. And the reason I like doing it this way is because we can be very specific with that network object group name. So I like to use some sort of naming standard. So maybe in this case, I'll do VPN-branch-local traffic. And this way I can see what the group name is for. In this case, it's a VPN. And then the next value is where the VPN is connected to. So in this case, it's going to be branch, but maybe that'd be the Portland office or San Antonio office or whatever your naming standard is. And then finally, what specifically we're protecting. So now that we have the group name, you could go and configure a network object member if it's not already configured, but mine already are. So go ahead and add that DMZ network by double clicking it, and then add the user subnet. That looks good, so I'll click OK. And then let's go ahead and expand network object groups, and then double click on it to add it for the value of our local network, and then click OK. For the remote network, we're just going to use one network object, so I don't need to go ahead and create another network object group, and I'll just type in the pre-configured network object that I created, and that's just going to be remote users. So just type in remote and then click on that value there. Let's go ahead and click next. All right, the ASA allows you to do a simple configuration where you just type in the pre-shared key and it'll automatically configure IKE version 1, IKE version 2, and all the corresponding default crypto sets. But I want to be a little more granular, so I'll go ahead and click Customize Configuration and then fill in all these values here. I don't want to use IKE version 1 because nowadays, most devices I'm working with all support IKE version 2, and it's more secure and has more features built into it. So now we need to tell the ASA how we're going to authenticate. And if you wanted to, you could use device certificate, but for this example, I'm just going to use pre-shared keys. So I'll enter the local pre-shared key of global123 with a capital G. And then to keep it simple, I'm going to enter that same pre-shared key for the remote side. Moving on to the encryption algorithms, by default, the ASA has selected all these algorithms. Personally, I don't think there's any reason to be using DES or triple DES, so I'm first going to go into the IKE policy and then configure these the way I want them. We are getting a pop-up here that these IKE policies are global, so keep that in mind when you're configuring these. I'll go ahead and click OK. So first you need to know that on an ASA, the ASA is going to always look at the policy with the lowest priority number first, even if that policy is less secure than another policy in that list. So just remember to always put your most secure policies first. And then personally, my stance is to remove all the IKE version 2 policies and then only configure them as needed for each VPN. Since this is the first VPN that we're configuring, I'm going to go ahead and select policy number 10 and then delete that and every other policy here. And finally, I'm going to modify this policy here as priority 1 and make it a little more secure. So I'll just double click it. All right, so for Diffie-Hellman group, we're going to use group 14. So I'll go ahead and select this, deselect 2 and 5, and then select group 14 and click OK. For encryption, AES 256, that looks good, but here are some of the other options that the ASA provides. Moving on to the integrity hash, might as well use SHA-256 since we have it. So deselect SHA and then SHA-256. And then finally, that pseudo-random function hash. Again, let's go ahead and change it to SHA-256. And of course, the more bits in these encryption algorithms and hashing algorithms, the more resources will be used on the ASA, and this all should work fine in a lab environment. So let's go ahead and select OK. And then finally, the lifetime is defined as 86,400 seconds, which is 1 day. I'll go ahead and click OK, and then click OK again. And then for the IPsec proposal, I can't actually delete these. Let me show you. If I click select and then try to delete some of these, I get a warning saying that these are defined by the system. So I'll click OK, and then I'll create an IPsec proposal that I do like by clicking add. And then instead of naming this IPsec proposal as the encryption, I'm actually going to name it as what it'll be used for. So I'll just type in branch VPN, and for the encryption, again, I'll set it to AES 256, click OK, and then for the integrity hash, let's go ahead and make this a little more secure and use SHA-256. So I'll click OK. Then I'll double click and add branch VPN. And then just to make sure we're not going to use any of these other ones, I'm going to go ahead and delete them and then click OK. And the last thing I need to configure is a perfect forward secrecy. And I do want to enable this. And then it needs to be configured as group 14. So I'll go ahead and click next. The last thing you need to decide is if you want to have the ASA automatically create a NAT exemption rule. But as you can see, even if we select this, we can only choose one interface for where we want this rule to come from. But for this VPN, we're going to send traffic both from the DMZ as well as the inside zone. And there's no way to manually specify which IP address is from which. So I'm actually going to deselect this and then manually configure that in a later clip. I'll go ahead and click next. And then here's a summary of the entire configuration. Everything looks good, so I'll go ahead and click finish. So here are all the commands that ASDM is going to send to the ASA. I'll go and expand this. So running through these commands, first, here's the object group that I just created with the 2 network objects that will go through the VPN. And this object group is referenced in the crypto map for this VPN as the local traffic. And then the remote users object is going to be referenced for the remote side. And of course, these 2 values are swapped on the remote firewall since its perspective is the opposite. And through the magic of video editing, this is what it would look like if I hadn't specified the network object group. Not so big of a deal with a single VPN, but if you have tens or hundreds of different VPNs all referencing different object group names, it's best to be as specific as possible to help when administering the ASA. Next, the group policy for this VPN is using an internal group policy, and then all attributes will use the default group policy, with the only difference being that I configured this VPN to only use IKE version 2. And here are the attributes of the tunnel group, the first line defining it as an IPsec site-to-site VPN, and the next two lines calling out the group policy and then specifying the pre-shared keys and keep alives. These commands are removing the crypto IKE version 2 policies that I didn't want to use, and then defining the IKE version 2 policy that I configured. Here is a configuration for the IPsec proposal that I configured using AES-256 for encryption and SHA-256 for the hash. And finally, these last commands are what ties all of this together. First matching the outside crypto map, then setting the peer IP address of the remote ASA, setting the IKE proposal to the one I created, configuring PFS, and finally configuring this VPN to use the outside interface. Remember that you don't actually call out the IKE version 2 policy, as the ASA will automatically run through all policies configured, starting with the lowest number, and run through them until it finds a policy that matches the policy of the remote ASA. Alright, so I'll send these commands to the ASA, and it looks like those commands were received. So now the VPN is showing up here in the site-to-site VPN configuration pane. So I'm good to go with the VPN that I want. And in my local network, I can see exactly what it is. And if I hover over it, I can see the values inside of that network object group. To make verifying connectivity while testing the VPN configuration easier, I will use ping requests for my testing. And if you're following along in your own home lab, you might want to use pings as well. However, by default, the ASA will not allow any ICMP traffic to flow through it, even if it is trying to flow from the inside zone to the outside zone. The reason for this is that ICMP traffic is not being inspected. To verify this, if I enter show run policy-map and then scroll up a little bit, you can see here the default global policy map that's automatically configured on the ASA and all of the different classes of traffic that are being inspected by the ASA. By default, TCP and UDP traffic is allowed and does not have to be explicitly configured in this default policy map. However, ICMP is not one of those protocols, and it does need to be explicitly configured to be inspected and pass through the ASA. So to fix this, I'm going to configure that policy map with the command policy-map. And if I do a question mark, it does require the name. And as you saw with the output of the running configuration, that name is global_policy. And then inside of the policy map, we're going to go into the default inspection. So that command is class inspection_default. And we're going to tell the ASA to go ahead and inspect that ICMP traffic with the command inspect ICMP. So now if we look at that policy map again, I'll hit spacebar to see everything. And then scrolling up within the global policy and the inspection default, you can see that we are now inspecting ICMP traffic. So if you've configured an ASA and you're wondering why ping traffic is not going through it, that's because by default, it is not being inspected. So the firewall will drop those packets. By allowing ping, this will make the testing of our VPN configuration that much simpler. The VPN's configured, so let's take a look and see if it's come up yet. To do that, I'm going to go to the monitor tab, and then here I'm in VPN, and then under VPN statistics and sessions. As you can see, nothing is showing up here, which is to be expected as there hasn't been any interesting traffic. So to generate some, I'm going to navigate over to Global Mantix's branch office computer and then open up command prompt. For this first test, will be a simple ping. I'll try to ping a computer that is sitting on the inside LAN of Global ASA 1. I want to have that ping continuously run, so I'll just do ping -t 192.168.17.254. I'll go ahead and let this run here, and as you can see, this request is timing out. So I'll navigate back over to the ASA and take a look at what's going on. If I click refresh down here on the bottom, this is good news as I can see that the VPN has indeed established. However, it looks like only the received bytes are incrementing. This means that ASA is receiving traffic over the VPN, but not sending it out over the VPN. I want to look at the firewall logs to get a deeper understanding. To do that, I'll just click on logging, and I'll leave the logging level set to debugging, and then click view. All right, we have a few logs here, and I'm going to go ahead and pause the real-time log viewer just to keep this clean. Let me go ahead and expand this. As you can see in the description, we are having an asymmetric NAT rule that is matched for this flow. Clicking on the description will give us a little more detail, but it's basically telling us the same thing. This traffic was denied due to NAT reverse path failure. To see why, let's go back to configuration, so I'll minimize this, and then click on configuration, and then navigate to firewall, and then here I'm already in NAT rules. As you can see, I already have a NAT rule that allows all internet traffic to go to the internet and NATing that internal traffic to the IP address of the outside interface. So the ASA thinks that the return ICMP traffic should also be NATed to the outside IP address and not maintain its original IP address. And that's why this traffic isn't working. So to fix it, that is why a NAT exemption rule needs to be created. To do that, I'll click add, and then I'm going to specify the source interface to be inside. And the source IP address is going to be that user subnet, so I'll just type in user. And the destination interface is going to be the outside, since that's where the VPN connection lives. And the destination address is going to be remote users. And as you can see here, under the translated packet information, we're going to leave that source address as the original IP address. All right, I'll go ahead and click OK. The last thing I want to do is to make sure that this rule is hit before that original rule. So I'll just go ahead and click the up arrow. So now this rule will be hit first, and I'll click apply to send these changes to the ASA. Go ahead and send them. So I'll navigate back over to that computer at GlobalMantic's branch office. And there we go. We can see that the reply traffic is indeed coming the way we expect it to. So now that we know that the connection to the inside LAN is working, let's test the connection to the DMZ. I'll just ping the IP address of that DMZ server. So shift the up arrow and then change the IP address to 10.100.1.11. And as you can see, this is timing out as well. Going back over to the ASA, I'm going to go ahead and open up those logs. Let's go ahead and resume them. And sure enough, this traffic is also having the same issue. So go back to the NAT rules. Let's go ahead and configure one more. This time, the source interface is going to be the DMZ. That source address will be the DMZ network. And then again, the destination interface will be the outside. And the destination address will be remote users. Go ahead and click OK. And then by default, this rule is automatically placed before the network object NAT rule. So it should be good to go. So go ahead and apply and send these changes. I'll navigate back over to that computer. And sure enough, I am seeing replies. So that all looks good. And finally, going back to the firewall, going back to monitoring, taking a look at the VPN, let this load here for a second. And now I can see that both transmitted bytes and receiving bytes are incrementing. And finally, going back to the real-time log viewer, I'll go and resume it. And this shows me another verification that traffic is working as expected. The Cisco Secure Firewall ASA has so many features to protect your network. Enterprises want to have redundancy in case one ASA goes down, so that way another ASA will be in place to continue to process traffic and secure the network. There are 3 different types of high availability options for the ASA. The first one is active standby, where only one ASA is active and processing traffic while the other ASA is standing by and monitoring the active ASA in case it should fail over. The second type is active-active, where both ASAs are actively passing traffic, although it's only for a specified context in the ASA. Both active-active and active standby are categorized as failover high availability, and I'll dive deeper into this in a moment. But the third high availability option is clustering. This is where 2 or more ASAs are all actively processing traffic without the need to use context like the active-active option. So let's dive deeper into each of them. With active-active HA, only one ASA, the active ASA, is passing traffic, and the standby ASA is just monitoring the active ASA to see if any of the failover conditions have been met. And if so, the ASAs will fail over, and then the standby ASA will become the active ASA and start passing traffic. There is no preemption for active standby. So this means that once a device is an active firewall, it will stay the active firewall until another failover event or until it is manually failed over by an administrator. The downside to active standby is that half of the ASA investment is just sitting there not in use. But on the other hand, it is the simplest to set up, and if an organization primarily cares about redundancy, this is a common option to use. Additionally, all ASA features are supported in active standby configuration. Active-active high availability requires the use of different device contexts on the ASA. So this is where the ASA is logically split up to have different functions, rules, and routing domains running on the same physical box. Active-active HA configuration is a little misleading. Sure, both ASAs are active, but only one ASA is active for a context, while the other ASA is a standby on that same context, and then those roles are reversed for the opposite context. The downside to active-active is that it is more complex to set up because multiple ASA contexts are required. However, it does make use of the second ASA to process traffic. For example, if there are 4 contexts, one ASA only has to process traffic for 2 contexts, while the other ASA can process the traffic for the remaining contexts, rather than one ASA having to process traffic for all 4 contexts if it's an active standby. And finally, ASA clustering is the most robust high availability option for the ASAs. So this allows for 2 or more ASAs to be actively passing traffic for all contexts. They're logically viewed as one ASA by the rest of the network devices. While this is the most robust configuration, it is also the most complicated to set up. Not only is it more complicated to configure on the ASAs themselves, the surrounding network devices need to be able to properly load balance the traffic to all the ASAs. Additionally, not all ASA features are supported with ASA clustering. Be sure to check Cisco's documentation to see which features are and are not supported before you implement clustering. But it will allow the most throughput of any high availability option, and it is the most resilient. There are requirements that need to be met before high availability can be implemented. All ASAs need to be the same model, and this not only applies to the chassis, but there needs to be the same types of and number of interfaces. They also must be in the same context mode, either single context or multiple context. And finally, they must also have the same major version number and minor software version number for failover HA, and clustering is even more restrictive as it requires the same exact software. So for my lab, I'm going to configure active standby as it is one of the most common HA deployments. The only changes needed for the network diagram is to add the secondary ASA. So now let's take a look at those 2 ASAs as a single logical ASA. To make this work optimally, for each data plane interface, I need to assign what is called a standby IP address. So for the outside interface, I'll use the outside IP address of 204.8.1.68. Since .67 is already in use for a NAT rule, the DMZ is simple as I have the standby IP address just be the next available, so that'll be 10.100.1.2. And on the inside, I actually need to make this a /29 to give me a third usable IP address. Then the standby IP address for the inside will be 192.168.18.2. All of these standby IP addresses will be in use by that standby ASA. And in order to make this work, I changed the inside router to a switch to accommodate both ASAs, and I changed the IP address on the switch from 192.168.18.2 to 192.168.18.3. The other configuration change needed is to add a link between the ASAs. I chose gigabit 03, and this will be the link to monitor each ASA to see if any of those failover conditions are met. These interfaces need to have an IP address, and since these aren't connected to the network, I just randomly picked 10.0.0.1 for the primary IP and 10.0.0.2 as the standby IP address, and both of those are on a /30. And then, if you want the state of the sessions to be monitored and replicated across the ASAs, another link is required. I used gigabit 04 for this, and the primary IP address is 10.0.0.5, and the standby is 10.0.0.6, again using a /30. Here's my EVE-NG lab, and if you're following along at home, I wanted to show you the changes that I had to make in order to configure HA. First thing I did was drop in Global ASA 2, and as you can see, I've connected Gigabit Ethernet 03 and Gigabit Ethernet 04 between these 2 ASAs. And then from there, I just mirrored all the other ports to go to the same destination. So gigabit 00 goes to the internet, the management interface goes to the out-of-band management network, gigabit 02 goes to the DMZ network, and then the only other change I had to make was for gigabit 01 to now go to the inside switch. And all I did there was put both ASAs in the same VLAN and then gave that VLAN an IP address of 192.168.18.3. And I had to change that from a /30 to a /29 in order to accommodate the standby IP address. From there, that inside switch connects to the inside network. So if you've been following along from the beginning, those are the changes you're going to have to make. So the first thing that we need to do before we configure the actual failover is to give the ASA a standby IP address on all the interfaces. You're going to do the vast majority of this configuration on the primary ASA. So I'm going to go to the CLI of Global ASA 1. All right, I'm going to enter configuration mode. And the first thing that I need to do is to go into each interface and then specify a standby IP address that the standby ASA is going to use until it's changed to the active ASA. So our outside interface, gigabit 00, it's going to be the same IP address. And then I'm going to enter the command standby and then add another IP address on that subnet. So 204.8.1.68. Same thing for the inside interface. I'm going to add the same IP address of 192.168.18.1. Again, this is now a /29, and I'm going to give it a standby IP address of 192.168.18.2. The DMZ network is going to be 10.100.1.1 again, and the standby IP address is going to be 10.100.1.2. And finally, the management interface is going to be 172.20.1.61/24, and this standby IP is going to be 172.20.1.62. So now that all of our interfaces have their standby IP addresses configured, let's go ahead and set up active standby. So I'm going to exit out of interface configuration mode. And now I first need to specify that I want this ASA to be the primary, which is different than active. Basically, we're saying we want all the configuration from this ASA to be pushed to that secondary ASA device. We'll do that with the command failover LAN unit primary. The next command is to determine which link we're going to use as a failover link. And that command is failover LAN, the keyword interface, and then you need to give this interface a name. I'm going to choose failover_link, all capitalized. And then I'm going to assign this to gigabit Ethernet 03. And as you can see, if this interface already had a configuration on it, the ASA would go ahead and wipe that interface and make it this failover link. So now we need to tell the ASA what IP address this interface should use. And I do that with the command failover interface and then specify IP and then the name of the interface. So I'll just start typing in failover and use a tab key. And I'm just going to throw away a /30. So I'm going to do 10.0.0.1 with a /30 and then again specifying the standby of 10.0.0.2. And if you want to have all the sessions pass back and forth between the active ASA and the standby ASA, you also need to designate a secondary link for that. So the command for that is failover link. And again, create a name. I'm just going to use sessions_link, all capitalized, and then specify gigabit Ethernet 04. And again, any configuration on that link is wiped. And finally, let's give that link an IP address. The command is failover interface IP, specifying that sessions link. Then we're just going to use the next /30. So it's going to be 10.0.0.5/30 with a standby IP address of 10.0.0.6. All right, that's the majority of our configuration. So now let's go ahead and enable both of these interfaces. So first, let's go into gigabit Ethernet 03 and enable it. And the same thing for gigabit 04. And now we need to enable failover by entering the command failover. So the primary ASA is configured. So let's go ahead and jump over to that secondary ASA. So go ahead and open that up. All right, and as you can see, this is a brand new ASA. So I'm going to go ahead and configure an enable password. But again, this is all going to be overwritten by that primary ASA. So I'll enter configuration mode, go and ask me later for that anonymous error reporting. And now let's go ahead and configure this. For this one, all we have to do is configure that failover link. And then from there, we're going to have that ASA push the entire configuration to this one. Pretty simple. So again, we need to specify that link with the command failover LAN interface. And I'm going to use that same name of failover_link, all capitalized. And again, that's going to be gigabit Ethernet 03. And then again, let's give it that same IP address with the command failover interface IP, specifying failover_link. And even though we're on the standby ASA, you still need to configure the primary IP address first, and then the standby IP address. So again, that's 10.0.0.1 with a /30, and then again, standby, and then 10.0.0.2. Let's go and enable this interface, exit out of interface configuration mode, and then to enable it, I'll enter the command failover. Let's give it a few seconds here. And as you can see, this ASA is detected an active mate, and it's beginning that configuration replication from the mate. If I go and go to the other ASA, first we have some messages here. When this ASA was looking for a mate, it didn't detect one. And then now that the configuration is complete on that other ASA, it has found that mate. It is starting to send that configuration to the other ASA. Let's go ahead and go back to that other ASA. And there we go. We can see that everything has been copied over. If I hit enter a few times, we can see that the name has changed from Cisco ASA to Global ASA 1. And what I like to do, just to make my life simpler, is to enter the command prompt hostname priority state. That way we can see which ASA we're working with. And here we can see we're on the standby ASA. So let's go back to that primary ASA. And again, enter that same command of prompt hostname priority state. And sure enough, we are the primary and we are the active firewall. The last thing I want to do is to enable a key so all this information is not sent in plain text. And I do that with the command failover key global 123. And because I'm configuring this on that primary ASA, it's automatically going to be pushed to that secondary ASA. So everything should be up and running. So if I enter the command show IP address, there you go. You can see all the IP addresses on this ASA, what's configured, as well as what is actually running on this ASA. If I enter that same command on that secondary ASA, it should be the opposite IP addresses. Sure enough, here are the primary IP addresses that are configured, yet since this one is that standby ASA, it is using those secondary IP addresses. And finally, let's go over to that inside computer. I'm going to pull up command prompt here. Let's go ahead and try to ping that primary inside interface IP address. And we're getting replies from it, so that looks good. So now I'll try to ping that secondary IP address. Give it a second for the ARP to resolve. And there you go. Both ASAs are communicating properly. To start this demo out, on the left hand here, I have a continuous ping from the inside computer to an IP address on the internet. And on the right is a continuous ping over the VPN to a computer that is running at the branch office. So let's jump over to our ASAs. And the first thing that I want to do is to tell the ASA to monitor the inside interface, the DMZ interface, as well as that outside interface. So if any of those links go down, the ASA will automatically fail over. The command to do that is pretty simple, and it's monitor-interface and then the name of the interface. So I'll enter it for the inside, use the up arrow, and then specify that DMZ interface, and then finally specifying that outside interface. All right, so everything should be monitoring, but before we test the links, let's just do a soft failover. And to do that, I'm actually going to jump to that secondary ASA, which is down here. I'm just going to enter the command failover active. All right, and as you can see, the primary is switching to standby, and that secondary is switching to active. Looks like that's complete. Let's go ahead and verify that. Sure enough, as you can see, on the primary, it is now the standby, and on the secondary, it is now the active. Let's jump back to that inside computer, and as you can see, those pings are still looking good, so we're good here. Jumping back over, now let's go ahead and test and make sure that link monitoring works. So I'm going to pull up my EVNG lab here, open up a CLI prompt for that inside switch, and go ahead and shut down interface gigabit 01, since that's the interface that's connected to the secondary ASA. All right, let's go ahead and minimize this and minimize this. All right, let's go ahead and watch and see what's going on with these firewalls. And there you go. You can see here that the primary is now switching back to active. So let's check our pings and see what's going on over there. And sure enough, there was a little bit of a request timing out. That's to be expected as it fails over. So let's jump back over and find some more information on those ASAs. On the primary ASA, I'm going to enter the command show failover. Actually, if I make this bigger, you can see a lot of good information here, such as, is this a primary ASA, the status of the failover LAN interface, how many interfaces are being monitored, the versions of both devices. But now, if we see some more information, you can see here that on the secondary device, it has failed because that insider interface has also failed. So that is why this failed over. I'll go ahead and minimize this to bring up the other ASA. So now let's go back to that switch and go and enable that port. And actually, before we do that, here you can see the switch did cycle through the EIGRP neighborship. So first it expired with the active ASA at the time when the link went down and the failover started. And then once the failover was complete and the other ASA became the active ASA, that neighborship was reestablished. So now, if I no shut the interface, it's now been enabled. So let's go back to both the standby ASA as well as the primary ASA and take a look. You can see that on the secondary ASA, it is now okay for the interface check. And again, we can verify that with the command show failover. I'll hit enter a few times, and now we can see that on the secondary ASA, that insider interface is showing as normal, which means that that ASA is now standing by and ready to take over if necessary. Here I am on the inside computer, and on the left, I have a continuous ping going to 8.8.8.8, so that's going straight to the internet. And then on the right, I have a continuous ping going to a computer sitting at the branch office, and again, that's going over the VPN tunnel between the headquarters ASA and the branch office ASA. So for this demo, I want to simulate a catastrophic failure of these ASAs. And to do that, I'm just going to shut one of them down. And here I am in the CLI of both ASAs. And as you can see, that primary ASA is the active ASA. So let's go ahead and shut that down. So I'll do that with the command of reload. It is prompting me that I want to proceed, and I do. So I'll go ahead and hit enter. And as you can see, this ASA is now shutting down. Let's give it a few seconds and we should see some messages coming from that secondary standby ASA. Sure enough, we can see that that ASA is indeed switching to active. And if we jump over back to our pings, we can see that there was some requests timing out. But again, as those ASAs communicated with each other and passed that session information back and forth, the outage was pretty small. Let's go back to our ASAs. And if I hit enter, sure enough, we can see that the secondary ASA is an active ASA. And again, there is that command show failover. Let me go ahead and make this a little bit bigger. And while this unit is a secondary unit, here is another verification that it is acting as an active firewall, and the primary firewall has completely failed. So we can see that here. But as that primary ASA is coming back online, we can see messages here showing that the configuration is being sent to the mate. And then again, these licensing messages are because I'm running in a lab, but we do see that that configuration was replicated to the primary ASA. And then to verify that, if I shrink this view of that standby ASA and then hit enter on the primary ASA, we can see that this ASA is back up and running and is a standby ASA. Here's a message on the primary receiving the replication from its mate. And then lastly, there is no preemption on the ASAs. So if you want to make the primary the active again, you need to go into global configuration mode. So I'll enter enable and then the password, and then enter the command failover active. And there we go. We can see that the primary ASA is now our active ASA. If you have a network environment that needs complete redundancy built in, but also have a high throughput of data, then ASA clustering might be beneficial. Clustering allows for 2 or more ASAs to be actively processing traffic all at the same time. And similar to an active standby configuration, one ASA will be the primary, while all other ASAs will be the secondary. The primary is determined by a priority number between 1 and 100, with the lowest number taking the priority. And this priority is determined upon cluster setup, so like active standby, there is no preemption. Once an ASA is the primary, it will stay that way until manually configured otherwise, or a failover event occurs to the primary ASA. Finally, the primary ASA is the one that performs most of the control plane tasks. So for things like dynamic routing, the primary will build out the routing table and then push that table out to the secondary members. It is also the ASA that configuration changes occur on and then pushes those changes to all other cluster members. So how does traffic flow through an ASA cluster? Well, the first ASA to receive a packet for a session becomes that session owner. And once an ASA is the owner, it will always be the one to process traffic for that entire session. And to help facilitate all traffic of the session going through the owner will designate a director by creating a hash of the connection details. The last role an ASA can have to process data traffic is the forwarder. If a cluster device receives a packet for a session that is not an owner for, it will use the hash details of the session to find the director, and once it's determined the director, the forwarder will communicate with the director to determine which cluster member is the owner of the session, and then forward the packet to the owner for normal processing. Of course, there is nothing preventing a director from receiving a packet itself, so in this case, it would query itself to find the owner, and then act as a forwarder to forward the packet to the owner. And this is just for one session. In an environment that justifies having an ASA cluster, each ASA could easily have thousands of sessions that it is handling. So for each session, those roles are determined accordingly. All of this communication is done via the Cluster Control Link, or CCL. Not only is this link responsible for determining the director and forwarding packets to the session owner, it is also the link that is monitoring the health of all cluster member devices, as well as pushing information from the primary device like device configuration or control plane information such as the routing table. All of these interfaces must be a dedicated interface, and they cannot be a sub-interface, and they all must be on the same subnet. On top of that, even in a cluster with only two ASAs, the CCL must connect to a switch rather than directly to the other ASA. This is so the ASAs can monitor their own interface status in the event that the interface fails on the other member ASA. The last thing to understand is what are the devices that are sending and receiving traffic to the ASAs. In an environment that justifies ASA clustering, there needs to be network resilience to make sure that the ASAs receive traffic in case devices go down, but also make sure the network is load balanced properly. There are multiple ways to do this. One is through the use of layer 2 technologies, such as virtual port channels connected to multiple switches, which is depicted here, or it could be done at the layer 3 level with either policy-based routing or equal cost multipath. And since all ASAs are expected to actively be processing traffic, the cluster needs all members performing at 100% to work reliably. If an ASA fails, or even if an interface on a cluster member fails, that will cause it to be removed from the cluster. If this is the case, for all sessions that the ASA was an owner for, the next ASA to receive a packet for that session will become the new owner for the session. And if the ASA was a primary member of the cluster, the ASA with the next highest priority, which again is the lowest number, will become the new primary device for the cluster. Enterprises use defense in depth to build out their security posture. Now that the Cisco Firewall ASA has been configured, let's integrate it with other security tools. The first tool that I'm going to integrate it with is Cisco's Identity Service Engine, otherwise known as ISE, and this will be used for TACX communication. This is so device administrators can be created in a single location, and then the specific commands that they can use will be pushed to all ASAs throughout the enterprise, rather than having to configure it locally on each ASA. And this clip doesn't dive deep into the configuration of ISE, so if you want a deeper understanding of how to configure it, check out the Cisco Core Security Secure Network Access using Cisco ISE course that is also part of this cert path. Here I am on the ISE server, so let's walk through everything that needs to be configured here before we can enable AAA on the ASA. The first thing we need to do is to make sure that TACX is enabled globally on the ISE server. And to do that, I'm going to click on the hamburger menu, and then under administration, and in the system settings, I'm going to click on deployment. I'll go into that global ISE node, and then I'm going to scroll down, and what you're looking for here is this checkbox, enable device admin service. So if you need to enable that, go ahead and do so, and then you just click save. So now the next step is to make sure that the ASA is added as a network device. So to do that, I'm going to go back to the hamburger menu, and this time go to Work Centers, and then we're going to spend the rest of our configuration here under Device Administration. And first, we need to go to Network Resources. As you can see, I've went ahead and pre-populated this. Let's go into one of them so you can take a look. First, I gave it a name of Global ASA 1.61, and then I configured the IP address to be 172.20.1.61, and then scrolling down, I classified this device type as firewalls, and for location, I put it in the headquarters office. These classifications here will allow your policy sets to be granular, as these can be match conditions for your rules. Scrolling down, the only thing we need to do here is to enable TACX authentication, and then for the shared secret, this will need to be entered on the ASA, and that's Global ICE 123 with a capital G, I, S, and E. So that looks good. Going back to the devices, I want to go ahead and discard the changes. That's fine. As you can see, I've created one both for the primary ASA as well as the secondary ASA. So once all the network devices are added, you need to make sure that the usernames and passwords are configured, since the ASA will be reaching out to ICE for that authentication. Rather than having those accounts created locally on ICE, I'm going to leverage Active Directory, so that way the administrators and help desk operators don't need to remember yet another password. That's configured under External ID Sources. And again, since it's Active Directory, that's located here. So let's go into that Global 81 Active Directory source. And it is operational, so that's a good sign. And then going into groups, I've went ahead and added the groups of IT, IT admins, IT help desk, and operations. Again, this will allow us to use these in our policy set. And before I show you the policy set, let's take a look at what the policy will return to the ASA. And that is under Policy Elements, and then underneath Results, and we have both TACX profiles and TACX command sets. Let's first take a look at the profiles. And then here I've created two profiles, one for the network administrator and one for help desk operators. So first, let's go into that network admin profile, click it, and then click Edit. And then scrolling down, the settings that I configured were to place any admin directly into default privilege 15, which is the highest. And I set the idle timeout for 10 minutes. But as you can see here, there's more options that you can configure. This looks good, so go ahead and cancel out of this. And then looking at the help desk operator profile, scrolling down, the only change here is that the default privilege is 4. And if you wanted to, you could add some custom attributes, but I'm good with all the defaults, so let's take a look at the command sets. I have different command sets for the help desk operators, whether they're logging into an ASA or an iOS device, and that's because they're more restrictive. So let's take a look at the ASA one. So I'll select it and then click Edit. And as you can see here, this command set is only allowing the commands Enable, Clear, Exit, More, and Show. And as you can see, I don't have any arguments defined for any of these commands, so that means that help desk operators will be able to use any subcommands. So for example, for the show command, they can do a show running config, they can show the IPsec SAs or IC SAs, or any other sub show command. If you did want to lock this down, you will need to explicitly add the arguments for which subcommands you want to enable, and then if it's not explicitly defined here, they will not be able to enter those commands. So let's go back to our command sets, and then take a look at the network admin commands. I don't have a separate one for the ASA and iOS because, as you'll see, these commands allow anything, as you can see here with the checkbox for permit any command that is not listed below. So since nothing's listed, these administrators will be able to enter any command. Now that we've gone through all the pieces to build the policy sets, let's take a look at that policy set. To do that, I'll just click on Device Admin Policy Sets. And then here, I already have one configured for ASA admins and operators. So let's go ahead and take a look at that in more detail. So right off the bat, the condition met here is the device just needs to be a firewall. So if you want to have different policy sets based on maybe the location of the device, you could go ahead and add another condition. And then here under allowed protocols and server sequence, I've selected the default device admin, which is a pre-built protocol policy set that includes TACX protocols such as PAP and ASCII, CHAP, and MS-CHAP. All right, so let's take a look at that authentication policy. Scrolling down, all we're doing here is we're just telling ICE to, instead of looking at a local internal user store on ICE or even all user ID stores, we're going to tell it to look at Active Directory. And then once the users have been authenticated, they need to be authorized. And that's done in the authorization policy. And scrolling down, you can see that I have 3 policies here. The first one is for the ASA admins. And so what we're doing here is the condition is looking to see which AD group that they're in. So as you can see for this one, we're looking to see if they're an IT admin. And if they are, they're going to be given the global network admin command set, which again is all commands. And then also that shell profile, which is privilege 15 with a 10-minute idle timeout. And the second rule here is checking to see if they're in the IT help desk Active Directory domain. And if so, they're going to be given global ASA help desk operator commands. With that shell profile, it's going to put them in privilege mode 4. I'm already in configuration, device management, and we want to scroll down and go into users and AAA. The first thing that we need to do is to define our server groups and the ICE server. So to do that, I'll click AAA server groups, and then under AAA server groups, I'll go ahead and click add. For the AAA server group, I'm going to give it a name of global ICE, and then I'll change the protocol from radius to TACX, then leave everything else set to the defaults, and then click OK. Now that the group is created, let's go ahead and select that, and then now define all of our TACX servers. So go ahead and click add, and I want to use the management interface to reach out to ICE, so I'll leave that selected, and the IP address for the ICE server is 172.20.1.55. I'm going to leave the timeout as 10 seconds, leave the default port of 49, and then here we need to specify the key that was configured on the ICE server, which again is global ICE 123 with a capital G, I, S, and E. That all looks good, so click OK. And then if you had multiple ICE servers, you could go ahead and add all of them here, and then the ASA would reach out to them by leveraging this group. So let's configure that last step. We do that under AAA access. So if you're with me earlier in the course, we did already enable ASDM and SSH access, but we told it to use the local database. So let's go ahead and change that to global ICE. And then here, I do want to leave this selected. So that way, if ICE goes offline, we can still get into the ASA by using that local database. However, let's go ahead and require authentication for the use of privilege mode commands. So check that box. And then again, defining the global ICE server we just configured, and then using the local database if ICE goes offline. Moving on to authorization, I'm going to check the box for HTTP as well as enable. And we are using the global ICE server group, but I do want to use the local database for backup. I don't need to create ASDM defined user roles, as we're going to let TACX and by extension ICE do the authorization for each command. And to round this out, we do want to use authorization for shell access. Again, that's a remote server. And we do want to allow privileged users to just go straight into exec mode without having to enter that enable password. That's just my preference. Go ahead and follow your policy. The last thing we need to configure is the accounting. And by now, you should guess exactly what I'm doing. Just going through, enabling the global ICE server to be used for accounting for any user activity, as well as any connections coming over the serial link or the SSH link. And then finally, I'm going to require command accounting for the ASA, again pointing to global ICE. That's everything that needs to be configured on the ASA, so go ahead and click apply. And then here we are getting a message letting us know that if everything is not set up properly, we're going to have issues. So not only with ICE accounting, make sure that authentication and authorization is configured properly on ICE before you enable it on the ASA. I'm confident with my setup, so I'll go ahead and click yes. All right, and here's all the commands. First, defining the global ICE server to be used with the TACX protocol, and then defining what the IP address of the server is and which interface it should use, and of course, the key that matches on ICE. Next, we're telling the ASA to use ICE first and then fall back to the local database if ICE is offline for authentication for enable, HTTP, as well as SSH. And then again, very similar commands, this time for authorization. And then finally, the same thing, telling the ASA to use ICE for AAA accounting. So I'll send these commands to the ASA. Okay, let's go ahead and test and make sure this is working properly. First, let's test the CLI. If I right click, I already have a session created for this active ASA. And I'm going to first log in with Brian as he's a help desk operator. So let's verify that he has limited access. You can see he's in privileged exec mode, so let's try a show command. That all looks good, but if I try to go into configuration mode, you can see here that command authorization failed. Let's go ahead and duplicate this session. This time I'll log in as Kinda, and Kinda is an IT admin, so she should have full access. And now if she tries to go into configuration mode, she is authorized to do so. Lastly, let's verify on ASDM, so I'll go ahead and cancel out of this, minimize my screens, and let's go ahead and launch the ASDM launcher. Again, first let's test Brian, and I'll enter his Active Directory password. I'm fine with a self-signed certificate, so click continue. And then once this loads, there you go. You can see that it doesn't even have the configuration tab because again, that is not even authorized. So the ASA knows that, so it's not even going to present it, but he does have access to that monitoring tab. So again, let's close out of ASDM. And one more time, opening up ASDM, going to log in with Kinda's Active Directory account. And then when prompted, click continue. And then once this loads, you can see that Kinda does have that configuration tab. And finally, let's go ahead and send one more command of write memory, and this should work. There you go, no errors. Everything is configured and working properly. Now I want to integrate Cisco Umbrella with the ASA so that way any users that are going to the web can have that traffic inspected and have another layer of defense in depth. Once again, Cisco Umbrella is not the primary topic for this course, so if you want to know more information about it, check out the Cisco Core Security, Content Security with Cisco WSA, and Cisco Umbrella course that is part of this skill path. Before you can send traffic from the ASA to Umbrella for it to be inspected before going to the internet, there are some prerequisites. One of the first ones is to import Umbrella's digital certificate. So I'm here on Cisco's documentation. I'm going to scroll down a little bit, and then here is that certificate. I'm going to go ahead and select it, but not include the begin certificate and end certificate section, and then copy that. So I'll minimize my browser, and then I'm here in the CLI, so let's go ahead and configure the certificate authority trust point for that Umbrella server. So enter configuration mode, and that command is crypto CA trust point, and then a locally significant name, and I'm going to use umbrella_server. Now we're in the CA trust point configuration mode, and I'm going to tell the ASA that we're going to enroll this manually by pasting in that certificate that we just copied. And to do that, I'm going to use the command enrollment terminal. And then to copy that in, the command is crypto CA authenticate, and then specifying umbrella_server. All right, and as you can see, we need to paste it in and then enter the word quit on its own line. So right click and then hit enter to get on a new line and then type in quit. The ASA is prompting me to make sure that we do want to accept this certificate, which I do, so go ahead and enter yes. All right, that prerequisite is completed, so now we need to configure Umbrella. In order for this configuration to work, it does rely on API keys, so I'm going to open up a browser and then navigate to my Umbrella dashboard. All right, to generate an API key, that's located under admin and then under API keys. And then once this loads, to generate the right type of key, we're actually going to go into legacy keys and then scroll down and then click on legacy network devices. From here, you're just going to generate a token. I've already got one generated from all the lab testing. So just to make sure we're starting fresh, I'm going to refresh this token. And I'm getting prompted, letting me know that any devices using this old key will no longer work. I'm fine with that, so I'll refresh it. And then scrolling down again, here's that new key, so let's copy it to my clipboard. Going back to the CLI, the commands to configure Umbrella are located under umbrella-global. And then we need to specify that token with the keyword token. And then I'll right click and paste that token in and hit enter. And then we are prompted that we need to make sure we have a DNS server configured that can resolve api.opendns.com, and also that we have a route to api.opendns.com. The root certificate of Umbrella is installed, and this unit has a triple-DES license. We're good to go on options 2 through 4, but in order to make this work, we do need to configure that DNS server. Before I do want to tell the ASA to not send any queries from globalmantics.com to Umbrella, since those would all be local queries and they don't need to go through the internet. All right, that is configured, so let's exit out of this. So we need to tell the ASA which interface to use for DNS lookups, and that command is DNS space domain-lookup, and then specify the outside interface. And then we need to configure a DNS server, and that command is DNS server-group, and then a name of default DNS. So to create the servers, that command is name-server, and then I'll specify Cisco's DNS server of 208.67.220.220, and then specify the outside interface. All right, that looks good. So let's exit out of this. And the last thing we need to do is to tell the ASA to go ahead and route any DNS queries to Umbrella to be inspected by that secure internet gateway. To do that, we need to modify the default DNS policy map. And so that command is policy-map, and then specifying the type, inspect, the keyword of DNS, and the map name of preset_DNS_map. And then we need to go into the parameters with the keyword parameters. And then finally, tell the ASA to use Cisco Umbrella. All right, that's it. This should all be good. So let's go ahead and end. And then to verify, I'm going to use the command show service-policy inspect DNS. All right, and that looks good. That's exactly what I'm looking for. As you can see here, the status is 200 success. So it looks like we are registered. We do have a device ID. And to show this another way, if I enter the command show running config policy-map, you can see here in the inspect DNS preset map that we just configured, the ASA automatically added the device ID here on that Umbrella line. Finally, let's close the loop and go back to Umbrella and make sure that this ASA is showing up there. So to do that, I'm going to click on deployments and then network devices. And then once this loads, there you go. You can see that this ASA is online. From here, just go ahead and configure that default policy that you learned in the Cisco Core Security, Content Security with Cisco WSA and Cisco Umbrella course here at Pluralsight. NetFlow is a great way to have an aggregate understanding of all the traffic that's flowing through the network, not just specific to one device. So in this clip, I'm going to configure the ASA to send traffic to the flow collector, so that way it can look for various anomalies in that network traffic. If you want to know more about NetFlow and specifically Cisco's StealthWatch, which is their solution for NetFlow, check out the Cisco Core Security, Secure Network Access, Visibility, and Enforcement course that is part of this cert path. Using ASDM to configure NetFlow is a pretty simple process. In this version of ASDM, the NetFlow configuration is located in the Configuration tab, Device Management, under Logging, and then finally NetFlow. The first thing that I need to do is to specify the flow collector that I want the ASA to send all the NetFlow to. So to do that, I'll click Add. And then I need to specify the interface, and I'm actually going to use the management network. And then the IP address of that flow collector is 172.20.1.53, and that collector is configured to accept NetFlow over port 2055, so that's what I'll configure. Go ahead and click OK. And then I do actually want to disable redundant syslog messages. That way the ASA doesn't spend as much resources duplicating syslog messages that could go over NetFlow. And then the other step to make this work is to configure a service policy rule to tell the ASA specifically which interfaces and what type of traffic it should send in that NetFlow data. To do that, go to Configuration, Firewall, and Service Policy Rules, and there's a convenient button here, so I'm just going to go ahead and click it. All right, we need to add a new rule, so go ahead and click Add. And then here you can specify if you want to have this policy rule for a specific interface or have it apply to all interfaces, which is what I want because I want all traffic to go to the NetFlow collector. So I'll leave this selected and then click Next. I'll leave the name set to global class, and then you can specify which specific match criteria you want to send to your NetFlow collector. I'm going to go ahead and select any traffic so that way I get as much data as possible, and then click Next. And the service policy rule wizard is not just for NetFlow, so let's go ahead and take a look at those NetFlow settings by going to the tab. And then here we need to specify that collector that we just configured. If you want to, you could get granular and specify the different flow event type, but I only have one collector, so I'm going to leave it selected to all, and then click the checkbox to send this information to that collector. Then go and click OK, and then click Finish. And again, we're getting a message asking us if we want to disable those redundant syslog messages. I already configured that, but I'll go ahead and click Yes. And then let's go ahead and apply these changes. All of these no logging messages is the ASA removing those redundant syslog messages. And then this line here is defining that flow collector over the management interface. Moving down, here's that class map that we just created, matching any traffic. And then finally, a policy map referencing that global class, and then telling it to send all the flow export information to the flow collector. So that all looks good. So go ahead and click send. And there you go. The ASA is configured to send the NetFlow data. When trying to upgrade an active standby pair of ASAs, Cisco recommends to first start out on the standby ASA. So I've went ahead and connected to the standby ASA using that standby IP address. And as you can see, I'm running ASA version 9.12.2, and I want to upgrade to 9.12.4. The first thing that you should do is check and make sure that your ASDM version supports the ASA version that you're going to connect to. And if it doesn't, update that ASDM version first, as long as it's backwards compatible. I'm good to go on mine, so I'm going to go ahead and navigate to Tools, and then Upgrade Software from Local Computer. The ASDM makes this a pretty simple process, as you don't have to worry about a file transfer server. So I'm going to browse to my local files, and then select the version I want to upgrade to. And then for image to upload, I need to change that to the ASA. And it goes without saying that if you're updating ASDM, you would select ASDM here. All right, I'm going to go ahead and upload this image, and I'll pause and then return when this upload completes. All right, that upload completed. And since we're on an ASA pair, Cisco recommends to not set this as the boot image. However, if you're upgrading a standalone ASA, you'd go ahead and click yes. But again, I'm going to click no. And then now I need to connect to the active ASA. So let me go ahead and do that here. Wait for this to load. And then I'm just going to follow that same process. So again, that's under Tools, and then Upgrade Software from Local Computer. Change this to ASA, navigate to the local file, and then click on Upload Image. Again, I'll pause and come back when this is finished. All right, this time when prompted to set this as a boot image, I'm going to go and click yes. And that command is boot system, and then it's going to specifically call out the file we just uploaded. So I'll go ahead and send that command. And then once that's been done, I'm prompted letting me know that I need to reboot the ASA in order for this new image to take effect. So go ahead and click OK. So now I want to go ahead and save these changes so that way when these firewalls do reload, the boot image is saved. And again, since I'm configuring this on the primary, that command was sent to the secondary device. All right, the next step is to reload the standby device. So to do that, I'll navigate to the monitoring tab and then click on properties. And then underneath failover, I'll click on status. And then finally, I'll go ahead and click reload standby. All right, the secondary unit's online. So let me go ahead and failover by clicking make standby on this ASA. I am prompted to make sure this is what I want to do. So I'll click OK. So now that the secondary unit is an active one, I am prompted to reconnect. So I'll go ahead and do that. So even though I am connected to the same IP address, you can see that this is the secondary ASA and it is active. So I'll go ahead and reload the standby ASA, which again was the one we were just on. We can see that both versions have been upgraded successfully. This unit is a secondary active device, and the primary is still the standby. So let me go ahead and make that switch one more time. So that way the primary ASA is the active ASA. All right, both ASAs are upgraded, and the primary ASA is the active ASA. While the Cisco Firepower ASA was traditionally designed to inspect and process traffic at the layers 2 through 4, today's threats require defense all the way up to the layer 7 level. That's why when Cisco purchased SourceFire to add layer 7 threat defense capabilities, they quickly made it available to integrate with existing ASA deployments. The ASA with the Firepower Services module gives the ASA next-generation firewall capabilities without having to swap out hardware to a dedicated Cisco Firepower appliance. It provides 4 distinct capabilities for inspecting and processing traffic that an ASA without it does not provide. Application visibility and control is one of the Firepower features that allows the applications to be classified and then policy created around them. Rather than just relying on ports and protocols, the firewall can now identify the specific application. more visibility means more control on what to do with these applications. The Firepower module also provides next-generation IDS and IPS capabilities, which has the ability to look for threats inside of the traffic, either based on signatures for known threats or look for specific traffic behavior and then take action on that as well. The Firepower module also brings another feature to the ASA, which is AMP for networks. AMP stands for Advanced Malware Protection, and its primary features are sandboxing suspicious executable files to look and see how they behave in that sandbox, as well as file trajectory tracking in case devices do become compromised. That way, organizations will be able to see how and where a malicious file travels throughout the network. And then finally, the Firepower module provides URL filtering capabilities for the ASA. This will allow organizations to determine which URL categories, as well as specific URLs, their users and devices are able to connect to. In addition to all the ability to restrict traffic based on applications, URL categories, and whether or not there's malware in the data, all of these additional features allows for more visibility into what is running on the network. The Firepower module includes a dashboard that helps administrators determine the overall security health of the network while also pinpointing specific problem areas that may need further investigation, or maybe see where the security is a little deficient and add additional policy rules to prevent the type of traffic that you don't want to see. Additionally, next generation features such as automatic cloud updates to signatures as well as global security threats is possible due to the unified threat management features. Now all the security data from multiple organizations can be looked at to help see global as well as regional trends, which benefits all Firepower customers with those security updates. And if an organization does have dedicated Firepower appliances, those appliances can be managed along with the ASA with Firepower services in a single management pane. So this allows for that next generation security policy to be pushed out to multiple devices at once, reducing the administrative burden of keeping the network secure. To wrap this course up, I wanted to cover a few more ASA deployment types that are available. All of these options that you've learned throughout this course and are about to learn are not mutually exclusive, and they are designed to be combined to be used with each other. And once you understand the basics, I'll walk through this example network diagram to see why some options would be deployed. While transparent mode is not the most popular deployment mode, it still occurs when the right use cases exist. Transparent mode is when the ASA is placed in an existing network to filter traffic based on policies. However, the interfaces do not have their own IP addresses in different subnets like they do in routed mode. So the ASA does not route the traffic, but acts more like a switch to just process the traffic. The ASA is just dropped in line into an existing network, and since it doesn't route the traffic, the network does not have to be reconfigured and a new IP scheme created. Transparent mode can be referred to as a bump in the wire, since most devices will not realize that there's a transparent ASA, even though it is still inspecting and processing traffic. There are a few different use cases to deploy transparent mode, and they revolve around not having to change the network IP space in order to inspect the traffic. One of the most common use cases is to place an ASA between an internet service provider router and their internal network. A lot of times, this will be a /30 between the two devices, and the main use case for this is to inspect the traffic and not implement something like VPNs or network address translation. Another use case is to implement network segmentation, again, without having to change the IP scheme. While not as common today, there are still existing networks that leverage legacy systems that cannot have the Layer 3 network changed. Another option that could be beneficial for organizations is to deploy their secure firewall ASA with the use of multiple contexts. As the name implies, multiple contexts allows a firewall to be logically separated into multiple virtual ASAs. This is true for both physical ASAs as well as virtual ASAs, which is what I've been running in my lab. Each context has its own set of rules, routing domains, and interfaces are assigned specifically to each context. For ASA appliances that do not have a lot of physical interfaces available, a common practice is to leverage subinterfaces and assign specific subinterfaces to the various contexts, which can make the investment in the supporting network smaller as well. And that's the main benefit of multiple contexts. While setting it up is more complex, the main benefit is it allows for a logical separation of roles for each firewall. Therefore, organizations don't need to purchase another ASA. For example, maybe there's a campus network that has multiple business units, and each business unit would have their own sets of policy administrators. Or it could be a service provider that has multiple different customers in their data center, so each customer would need their own rules. Or it could just be a smaller organization that simply doesn't have the budget necessary to justify multiple physical devices, but would like a separate ASA to manage traffic at the edge of the network, while also having another context to manage traffic going in and out of the data center. Whatever the justification, multiple context provides flexibility in how the ASA is deployed while decreasing size and overall network footprint. So let's walk through a revamped network diagram with various ASA deployment options. First, I have the headquarters office with various data center clusters, as well as a network for users and a separate network for any guests. And both the user networks and guest network connect to a switch, which then connects to a pair of ASA firewalls running in active-active mode with a context for the users and then a different context for the guests. And remember that with active-active, each firewall is only active for one context while it is standing by for the other context. This firewall is connected to the internet, and since this is the headquarters office, they've invested in the firepower module to get next-generation firewall features. And the data center clusters connect to the core switch, which are then processed through a cluster of ASAs, each with their own contexts. This way, different policies and rule sets can be created for the various data center clusters. So, users going to the data center clusters will be processed, but also the inter-cluster processing will also need to go through the ASA. So that completes the headquarters office. So now let's focus on the new branch office that is being set up. Just users are located here, so no need for any data center firewalls. But they do need to go out to the internet, so that traffic needs to be protected. So as you can see, they are connected to the ASA via a switch and then out to the internet. This branch does necessitate high availability, but not multiple contexts, so this will be an active standby configuration. Additionally, this site doesn't need the firepower module at this time, but they do want to implement URL filtering, so they will send web traffic to Cisco Umbrella. Finally, a site-to-site VPN between these two ASAs does need to be created so the users at the branch office can get to the resources at the headquarters site. Lastly, there is the legacy data center location. This site will be decommissioned in the near future, and the applications will migrate to the data center at the headquarters office. There is already a site-to-site VPN between a Cisco router and the headquarters ASA. So in the meantime, these legacy applications cannot have any changes to their IP scheme. This is an old site, and it just used ACLs on the router to allow customer traffic in. But the company wants to protect the network a little more, so it's going to put a transparent ASA in place to have more features, along with better visibility into the traffic that is going to this site. The last thing that I will add is that unfortunately, designing a network is not a one-size-fits-all scenario. It is highly dependent to multiple factors such as existing network design, the budget, and the technical skill set and available time to be engineered and managed. As much as the nerd part of me doesn't want to admit it, sometimes simple is best, even though it isn't as much fun to design and configure. All right, that's everything I wanted to teach you. I know that your time is truly important to you, and from the bottom of my heart, I want to say thank you for investing it with me, and I hope you have gained something from this course. Unfortunately, sometimes things just don't work out the way you expect them to with any network device, and that's true for the Secure Firewall ASA. This module will walk through some troubleshooting tips, upgrading the ASA, and then various ways to deploy it based on the network requirements. So you think the ASA is configured correctly, but traffic isn't performing the way that you think it should. It's time to start troubleshooting. And people have different ways they go about troubleshooting, but I like to start with a simulation of a packet to see what the ASA will do with that packet. And that command is packet-tracer, keyword input, and then you need to specify what the ingress interface will be. So I'm going to simulate traffic from the inside network to the remote network. So I'll use the inside interface. And then you need to specify the protocol. I'll just use TCP, and the source IP address, and then the source port, so I'll just use a random one here, the destination IP address, and then the destination port. So what's cool about this is you can walk through the ASA's logic. So the first phase here is that we have an unnat rule to make sure that this packet stays as original IP address, and that's both for the destination as well as the source. If I hit spacebar to see a little more. Now we walk through all the different phases, and the thing you're looking for here is the result, and so we have a bunch of allows. Phase 7, we're going over the VPN, and it's going to be encrypted. Again, allowed, that looks good. And then continuing on, eventually you get to the bottom with the final result, and in this case, everything is allowed, so it looks good. However, sometimes this command can be a little misleading, because if I try to simulate that return traffic, even though it goes through the VPN, the ASA will think it's a brand new session coming in the outside interface. I'll show you what I mean. This time, the ingress interface will be the outside, and then the source address will be on that remote network, while the destination address will be on the inside network. While it does pass phase 1, you can see here that phase 2, this traffic is automatically dropped. It does give you a drop reason that the flow is denied by a configured rule. So this isn't always the greatest for VPNs, but just any other traffic that you're expecting to work properly, it's where I like to start to see how the firewall is making decisions. Another command that I like to use is show con to see all the connections. Whoops, that should be show con with 2 N's. And it's just a good way to see which connections are active flowing through the ASA. And if you want more information, you can enter show con detail, and that'll have more flags that you can look at for each connection status. I know we're looking at flows that are working, so let's take a look at some other commands to troubleshoot connections that are not working. One of the commands that I like to use to see drops on our interface is show interface, and the ingress interface, and then enter pipe, and then specify the keyword include, and then packets dropped. This is an outside interface, so I'm not surprised to see a bunch of packets dropped, but if you want to get a real-time look, go ahead and clear those statistics with the command clear interface gigabit 00. And let's take a look at the packets dropped again. There you go. So if you're expecting something to come in, you can quickly see if these are old statistics or if this is part of the current problem. But obviously, this doesn't give you detailed information. It just shows you counts. If you want to look for all packet drops across the entire ASA, that command is show ASP drop. And ASP stands for Accelerated Security Path. And this will give you the various reasons of why packets are getting dropped. So these last 2 commands do only show the counts. So if you want some more detail, you're going to need to set up a packet capture. So let me go ahead and do that with the command capture. Then I'll give it a locally significant name of packet drop. And we're going to specify the type. And we want to use an ASP drop again. If I enter a question mark, you can restrict this with an ACL list so you can get granular. And then scrolling down, you can actually look for specific reasons if you know exactly what you're looking for. But just to show you what it would look like, I'm going to go ahead and just put in an ACL drop. Now that the capture is created, let's go ahead and view it with the command show capture and then packet drop. There you go. You can see why this ASA is dropping these packets. It is because the flow is denied by a configured rule. So then from here, you just go ahead and check out your ACLs and make sure it truly is configured the way you expect it to be. I'm going to go ahead and clear that capture so that way I'm not taking up additional resources. And then finally, sometimes you just got to look at the firewall logs. So to do that, enter the command login enable. Whoops, I need to be in configuration mode. And then I'll set the logging level to debugging. And then here to look at it, you're going to enter show logging. And then here's everything that's going on the ASA, which is a lot of information. So you might want to parse out some information. So if I hit the up arrow and then I do a pipe, I can include anything with the keyword deny. And this is nice because the ASA is actually telling you which ACL is denying the traffic. You can also include specific syslog messages if you're looking for something in particular. I want to look at the ICMP logs, so then I'll enter 30202 star so I can filter on any syslog messages starting with 30202. So in this case, we're just looking at all the ICMP messages. But having an understanding of different syslog messages and the syslog numbers that correspond with them can help aid you in your troubleshooting efforts, and that's all found in Cisco's documentation. And then once you are done with your troubleshooting efforts, the last thing I'll say is to make sure you clean up. So in this case, I want to turn off logging to not consume too many resources on the ASA, and I'll simply enter the command no logging enable.